Hello, everybody. I wanted to describe an application of cosets to permutation groups. Another name for this is the orbit stabilizer theorem. So I'm building up to the orbit stabilizer theorem. We're actually gonna use the orbit stabilizer theorem on a couple of examples, and then in the next video, I'll give you the theoretical introduction to the orbit stabilizer theorem. So the orbit stabilizer theorem is an easy way to count the number of group elements in the group of symmetries of a shape, such as this dodecahedron here. How many symmetries do we have of the dodecahedron? How many ways do we have to rotate or flip this dodecahedron and get the same shape back? Well, what group that is might be complicated to figure out, but the size of that group is relatively easy to figure out using the orbit stabilizer theorem. Okay, so the two examples we'll do are the rotation group of the cube and the rotation group of the soccer ball, as I have drawn here. We'll count how many rotations there are mapping the cube to itself or mapping the soccer ball to itself. So this analysis won't describe the exact group structure, but it'll tell us the size of the group. Okay, so first example, exercise 9 out of our book. Let G be the group of rotational symmetries of a cube. So here's our cube. Oh, I'm having trouble orienting this. Okay, here's our cube. And then we can rotate it, for example, like that. We could rotate it, for example, like this. We could rotate it, for example, like that. We're looking at the rotations that fix the vertex set and fix all the edges. And so when you rotate it, after you're done, the cube comes back into the same position where it started. What's the size of this group of rotations? We'll figure out that this group of rotations has size 24, as I'll explain. All right, so this cube has 6 faces, and each rotation can be seen as a permutation of those 6 faces. So the 6 faces are getting swapped around. We're permuting the 6 faces. So maybe this is face 1, and as I rotate the cube, face 1 gets mapped to a different location. So the size of this group of rotations can be counted as follows. Fix your favorite face, maybe this front face here. We're only first going to count the number of rotations that fix this first face. Okay, so this is this term right here. What are the number of rotations that fix the first face? Well, if I want to fix the front face, there's only 4 rotations that fix it, right? Any other rotation sends the front face somewhere else. But if I want to fix the front face, there's only 4 rotations that fix it. Okay, that will be called the stabilizer of the front face, as we'll see in a moment. Okay, so you need to pick your favorite face and count the number of rotations that fix that face. In this case, it's 4. And then you also need to count, well, what are all the different faces that this front face could get mapped to? And it turns out this front face could get mapped to any other of the 6 faces by some rotation. So the number of faces that this first face could get mapped to is 6. The total number of rotations is going to be the product of those two numbers, 6 times 4, or 24. This doesn't depend on the fact that we chose the front face. If we chose a side face, the number of rotations fixing that side face is again 4, and the number of different faces this side face could get mapped to is again 6. It's called the orbit stabilizer theorem because this term here is going to be the size of an orbit, which we have yet to define. This number here will be the size of the stabilizer group, which I'll define at the very end of the video today. And so we get that the size of the group of the rotations of the cube is 6 times 4, or 24. This is correct. It turns out that the group of rotations is isomorphic to S4, the permutations of four elements. and the size of S4 is 4 factorial, or 24. If you want to know exactly why the group is S4, that's a little harder to see. Just a side comment is there's actually 4 diagonals in the cube. So diagonals going from one vertex to an opposite vertex. Here, let me do a better job of showing this. There's 4 diagonals in the cube. Here's one diagonal going from this vertex to the vertex I'm holding. There's this diagonal, there's this diagonal, and there's this diagonal. And S4 appears. It turns out that any rotation is a permutation of those 4 diagonals. All right, so in summary, we wanted to count the number of rotations of a cube. We picked our favorite face, any face, say the front face. We saw that there were 4 rotations fixing that face. That will be the size of what we will call the stabilizer. We saw that there were 6 different faces that front face could get mapped to, and that will be what's called the size of the orbit. And the size of this rotation group is the product of those 2 numbers. The size of the orbit times the size of the stabilizer, here 6 times 4, or 24. Let's do another example. Let's look at the group of rotational symmetries of the soccer ball. Here's my clip art soccer ball. So I want to map a pentagon to a pentagon. When I rotate, I need to map a hexagon to a hexagon, etc. I need to fix the stitching on the soccer ball when I rotate it. So what's the size of rotational symmetries? We can use the orbit stabilizer theorem, which we'll see in the next video, to count the size of this group in 2 different ways, actually. The first way, let's pick our favorite face to be a pentagon. So here's this front pentagon. First, let's count the stabilizer, the number of rotations that map this pentagon to itself. And you can see that there's 5 rotations mapping this pentagon to itself and fixing the stitching on the soccer ball. Okay, so the size of the stabilizer is 5. What's the size of the orbit, the number of pentagons that this fixed front pentagon could be mapped to? Well, it turns out that in a soccer ball you have 12 pentagons. You can see 6 of them here, and the other 6 are on the back face. So there's 12 different pentagons that this front pentagon could get mapped to. Okay, so the size of the entire rotational group of symmetries is going to be 12, the size of this orbit, times 5, the size of this stabilizer, which is 60 in total. That's the correct answer. The group of rotations of the soccer ball turns out to be the alternating group on 5 elements. The size of the alternating group on 5 elements is 5 factorial divided by 2. Remember, the symmetric group on 5 elements has size 5 factorial. So that's 120 divided by 2, or 60. So we haven't proven that this group is A5, but we have used the orbit stabilizer to at least find some clues about this group, that it has size 60. How would this change if I instead chose my favorite face to be a hexagon, like this hexagon in white right here? Okay, so we better get the same answer. The size of this group is still 60. We're just going to be counting it by a different technique. So what are the number of rotations in this group of rotations of the soccer ball that fix this hexagon? You might think this hexagon has 6-sided symmetry, so there's 6 rotations, but that's not right. Only 3 of those rotations actually fix the stitching of the soccer ball, right? If I rotate this hexagon by only 1/6 of the way around, I'm trying to map this pentagon here onto this hexagon. So that's not fixing the stitching. To preserve the stitching, I need to rotate by 1/3 of the way around, mapping this pentagon to another pentagon. And then I could do 1/3 of the way around again, mapping this pentagon to this pentagon. So the hexagon itself has 6 symmetries, rotational symmetries, but if I require the stitching on the entire soccer ball to be preserved, there's only 3 rotations, okay? So only 3 rotations, preserving the soccer ball, also map this hexagonal face to itself. So that's why the size of this stabilizer here is 3. How many hexagons could this hexagon get mapped to? Well, it turns out that there's 20 different hexagons in the soccer ball. You can see 10 of them here, and then there's 10 on the back face. So there's 20 different, the size of our orbit, we'll call it, will be 20. So the total size of this rotational group is going to be 20 times 3, or 60. So we got the same answer, the right answer, 60, whether we focused attention on a pentagonal face or a hexagonal face. And even though I haven't told you the orbit stabilizer theorem yet, this will be an application of the orbit stabilizer theorem, allowing us to count the sizes of certain groups. Okay, let me end by beginning to introduce you to stabilizers. In the orbit stabilizer theorem, there's 2 main things I need to tell you about: stabilizers and orbits. Let me start with stabilizers. So G is a group of permutations of a set S. So for example, G might be the rotational group of the cube, and that can be thought of as a permutation group of the faces of the cube. Or G might be the rotations of the soccer ball, and those can be thought as permutations of, say, all the pentagonal faces, or instead permutations of all the hexagonal faces. So for each, so let's look at the cube, for example. So the cube, G is the group of rotations of the cube, and we're thinking of each rotation as a permutation of the 6 faces. So for each I in our set of things that are being permuted, so for each face, we're going to define the stabilizer of I in the group to be the following. The stabilizer of I in our group G is the set of all group elements that map that element or that face to itself. So here, the stabilizer of this front face is all the rotations of this cube that map the front face to itself. There might be other rotations of the cube, but we're only looking at the rotations of the cube that map the front face to itself. Okay, so in this example, if G is the rotational symmetries of the cube, then the stabilizer of the front face is just going to be 4 rotations. Okay, some other rotations are not included. I'm sort of using notation from the rotations of a square, but I'm just saying that the stabilizer is isomorphic to just having 4 rotations rotating this front square. The stabilizer will always be a subgroup of the entire group. So here the entire group is all rotations, right? It has 24 elements we saw. The stabilizer is just going to be a subgroup. Here the subgroup had size 4. 4 rotations fix the front face. All right, so let's talk about S3. This is the group of permutations of 1, 2, 3. So it's clear what's the set that this group is permuting. S3 is permuting the set whose elements are 1, 2, and 3. So what's the stabilizer of this group? What's the stabilizer of 1 under this group? Well, what are the permutations that fix 1? Just the identity permutation or swapping 2 and 3? If 2 and 3 swap, 1 doesn't move. Another example, what's the stabilizer of 2? It's just the identity permutation, or 1, 3, the permutation swapping 1 and 3. That doesn't move 2. The stabilizer of the element 3 will just be the identity permutation and the swap 1, 2, which doesn't move 3. If our group is S4, S4 permutes the set whose elements are 1, 2, 3, and 4. So what's, for example, the stabilizer of element 1? Well, the identity permutation doesn't move this element 1. Swapping 2 and 3 doesn't move this element 1. Swapping 2 and 4 doesn't move this element 1, etc. The cyclic permutation, 2, 3, 4, doesn't move the element 1. So, in disjoint cycle form, the permutations that don't move element 1 are going to be the permutations that don't have 1 listed in their representations. Okay, so let me give you a hint at one thing involved here. The stabilizer will always be a subgroup of the larger group G. So I have a group of permutations of my 6 faces. I fix my favorite face, my ith face, maybe this front face. The stabilizer will always be a subgroup. And we learned that the size of a subgroup always divides the size of the larger group. That was Lagrange's theorem. So the reason why 4 is dividing 24 in this product, 6 times 4 is equal to 24, is because this is the size of a subgroup of the group of all rotations of the cube. And the size of a subgroup, here 4, divides the size of the entire group, which has size 24. Or for example, in the soccer ball, the rotations that fix this front pentagonal face, that's a subgroup of the entire group of rotations. And that's why 5 here, the stabilizer subgroup fixing this pentagonal face I, divides into 60, the size of the entire group. That's Lagrange's theorem. Okay, so to end this video, I have not told you the orbit stabilizer theorem. I haven't defined orbits for you, but I've given you examples of how to use the orbit stabilizer theorem. You can use the orbit stabilizer theorem to count the size of a group by focusing attention on one element or one face and counting that group elements that fix that face and how many different places that face can get mapped. Okay, so we use this to count the size of the rotation groups of the cube, which was size 24. We use this to count the size of the rotation group of the soccer ball, which was size 60. And then I defined for you what the stabilizer of an element I is in a group G. And we'll get more practice with this in the next video, where we also introduce the orbit, and then we rigorously define the orbit stabilizer theorem for you. Okay, thanks. Bye-bye.